Okay, so good afternoon. Today's lesson is about factorization. It is not completely new. This is more or less a completion of what we learned before. So what do I mean by factorization? Let me start with a very simple setup. So when I say, when I give you a number, say for example 12, and I ask you to factorize 12, what do I mean? I mean to write it as a product. Yes, that is what I mean. For example, you can write 12, of course, as 10 plus 2. This is a true equality. But this is not what I mean. I mean, for example, to write 3 times 4. So this is not called a factorization. Even though this is true, this is called a factorization because not only 12 is equal to 3 times 4, but 3 times 4 is a product. So when I ask you to factorize a number, I mean that write it as a product. And of course, implicitly, I mean factorize it as much as possible. So even though 3 times 4 is a factorization of 12, but when I ask you to factorize 12, I do not mean to stop here. You have to factorize it until you cannot factorize it to more products. So it means that to factorize until your ingredients are prime numbers, yes? So in this case, if I want to factorize this, you would write it like this, or of course, preferably, you write 2 to power 2 times 3. Yes? So this is the meaning of when I say factorize a number. And now, of course, we already know how to factorize numbers, but we want to learn how to factorize polynomials. Yes? And then we have different techniques that we need to develop. As first of all, I just want to tell you that factorization is not a very simple task to do, but there are some basic things that you can learn and then factorize it. Yes?
So, just to be clear, you wouldn't consider just 3 to 4 as like properly or
fully factorized. And I
want it to be as many terms as possible.
Yes.
Okay.
Yeah. Okay. So, for example, the main rule behind factorization is the distribution law. Yes. For example, if I give you A times B plus A times C, it is not a factorized expression because this is the sum of two numbers. One number is AB, one number is AC. So what you read this is this is a sum, not a product. But you know that you can write this in this form, A times B plus C. We know that this is one of the properties of real numbers, that you can multiply this product inside a sum and write A times B plus A times C. But now if I ask you what is this, you say this is a product. What is this? This is a sum. This is not in factorized form because this is a sum, but this is in factorized form because this is a product. So this is the important rule behind factorization processes that we want to learn. That's the distribution law of multiplication over addition. From here, if you read it from right to left, it is distribution. I am distributing multiplication over addition. If you read the same equality from left to right, we call it factorization. I am factoring A out. This is the common factor. Yes? Okay, this is the first trick that you need to learn. You have the sum of some expressions, they share something in common, they share a factor in common, you factor that out. Yes? So let us just try to do some exercises in this regard. So, example. So factorize. Again, when I say factorize, I always mean fully factorize. So number one, for example, I have a squared b plus ab. I ask you to factorize this expression. So what are the factors in common? I have here, if I ask you how many factors are involved here, you would say 3 factors, 2 of them are a, 1 of them is b. Here I have 2 factors, 1 a and 1 b. So what are the common factors? A and B are common factors. So I pull A out and B out. By pulling out, I mean that you need to divide each one of them by this thing that you pulled out. For example, you need to have in your head like this. You say that I pulled AB out. It means that I divide this expression in my head, but what I pulled out. So what is left? B and B are cancelled. This becomes A, so A is left. And then I have addition. Again, I have AB here. So AB divided by AB. The answer is what? A and A are cancelled. Cancelled, it doesn't mean 0 is left. I am dividing. So what is left? 1. I am dividing a number by its own. So this becomes 1. So that is the factorization of this expression. And it doesn't hurt, always double check that you are doing things right by actually understanding that if I multiply this back, I will get the same thing. Yes, AB times A becomes A squared B, that's correct. AB times 1 becomes AB, so that is the fully factorization form of that. So this is the first trick that we learn in factorization. If there is something in common, if there is a factor in common among all of the terms involved in that expression, take the highest common factor out from all of them. Yes? So let me give you another example. So for example, I have 5acx plus 15cx. Okay? So what can I pull out here? You see between numbers 5 and 15, what is the factor in common? 5. A is not in common. C and X are again in common. So what can I pull out from the numbers? I can pull out a 5. A is not in common, but C and X are in common, so I pull them out. And then again in your head, you divide this expression by the expression you pulled out. 5 divided by 5, 1, C divided by C, 1, X divided by X, 1. So there is only one A left. You just write A here. And the sign between them is addition. You just write that. And then divide this in your head by that one. 15 divided by 5, 3 times. C divided by C 1 times. X divided by X 1 times. That's end of the story. And you double check it by multiplying it back if you want to. You multiply this back, you really get this one, that's correct. If you multiply this by that, you really get this one, that's correct. That's the first trick that you learn. For example, you might also have this one. So let me write another example. 45x to the power of 3y minus 77 x to the power 2y. And then finally I will have minus 63xy. So I ask you to factorize this. So you realize, is there something in common between numbers? Nothing is in common between numbers, yes? Because you see that these two numbers have a factor of 7 in common. But 7 is not a factor of 45. I don't know. 45 has factors of 5 and 9. But none of them are factors of these two numbers. So here I cannot pull any number out, can I? No. So forget about numbers. But then you see that I have 3 powers of x here, 2 powers of x here, 1 power of x there. So the maximum power of x that I can pull out is just 1x. So I just write 1x. I have 1y here, 1y here, 1y here. So I just pull y out. And then it becomes 45x squared. Because 1x is pulled out, 2 of them are left when I divide. Y is pulled out, 1 is left, so I don't write 1. I just write like that. And then it becomes minus 77xy. And then finally, x and minus 63. Yes? Any questions? Of course, this is always a question. How should I know that this is not going to be factorized more? Yes, we will be able to answer these questions a little bit later. But for the time being, that is enough for our purposes here. Okay, another thing that I want you to learn is that this kind of factorization. So this is also important. So sometimes we have expression like this. Yes? Okay, I want to factorize thing here. So you see that the first term is itself in factorized form. The second term is also in factorized form. But the total expression is not actually in the factorized form here, because that's a subtraction. Either you can continue or that is the end of the story. We just stop here. But here, if I ask you what are the factors involved in the first term, one factor is x itself, the other factor is a plus b. If I ask you what are the factors involved in the second one, there are three of them. One of the number 3, y, and a plus b. You immediately realize that a plus b as a whole is a factor which is common to both of them. So you can take this out. So I will take a plus b out. Again, I divide this expression in my head. If you want, I can write here x times a plus b. I divide it by a plus b. Whatever this number is, that is the same number. When I divide, these two are gone, regardless of the value. So what is left is just x. So I open, and if I pull this out, x is left from here. I can close the pair of brackets. If I do the same thing here, minus 3y is left. So the answer will be minus 3y. Yes? Okay, so let me give you another example and then we move to the second technique. So number 5. So let me write this. 4a, and then I have 3x minus y totally to power 2 minus 6ax multiplied by 3x minus y, and then I have plus 10ay, and then 3x minus y. So you want to factorize this. What we are supposed to do? That's a good idea because this is just a repetition of what we have learned. I pause recording and I give you 2 minutes to do this out. Yes. Factorize this, and we are just learning the first trick. The first trick is to be able to recognize the common factors and then pull them out. Okay, so what we are supposed to do? So what are the common factors? Between numbers 4, 6, and 10, it's not hard to realize. What is that? Only 2 is in common. So we took care of these numbers. But what about a? Is a factor in common? Yes, I see a 1 a here, 1a here, and 1a there. So a is also some factor in common to all of them. Okay, but x is not a factor in common because it is here but not here, not there. Y is not a common factor. It is here but not here and not there. And there is another common factor. What is that? Yes? 3x minus y as a whole is a common factor. How many of those factors appear here? 2 of them, but 1 of them here, 1 of them there. So how much is in common? Exactly 1. So I take this out. Okay, and then you open a pair of brackets in front to see what is left and write it there. So you need to divide in your head. So 4 divided by 2 is 2. A divided by A is just 1. You just write multiplied by 1, but no one writes that. And then here you have 2 factors of 3x minus y. One of them is gone. When you divide, one of them is left. And don't forget to put pair of brackets around that. Okay? The next one is negative. And then you do the same thing. You divide 6 by 2, it's 3. A divided by A, it is 1. Multiplied by 1, I don't write it down. X is only here, so X is left. I had 1 factor of these. I divide by 1 factor, so nothing is left. So minus 3x is the only one which is left from the middle. Okay, and then let us do the next one quickly. What is the answer? It's 5y. Do you agree? Yes? So, if I ask you, did you factorize this? The answer is yes, because now you have written as a product. But no one, I told you that this is not part of the question. I just write factorize. Factorize means fully factorize and simplify as much as possible. So this, I will call it a mess here. because we have unnecessary pair of brackets inside another pair of brackets. So you shouldn't leave it at this part. So you should simplify it. And this is, by the way, crucial. I will tell you why. So here, I copy and paste all these parts. But then I multiply this in. It becomes 6x minus 2y. And then it becomes minus 3x plus 5y. The reason that I do that, because I can simplify it more. So this becomes 2a, 3x. So be careful. Factorization is finished at this here, at this stage. The rest of it is simplification. Write it in a more reasonable way. Okay? So I would just open it. 6x minus 3x is 3x. And then now you see what happens here. Because this was not, we were not able to foresee this from the beginning. So if you stop here, that's not complete again. Here it's a coincidence. Because now what happens, you have 3x plus 3y, suddenly you can factor a 3 out again, which was not evident from the beginning. So that's a good example. Okay? First of all, it teaches you that you shouldn't leave it like this, even though apparently factorization is finished here. But you need to continue to simplify. One reason to do this, because it might happen the scenario that you need to be able to, you need to factorize it again. So I pull a 3 out from here. So what happens? This 3 that I am pulling out will be multiplied here. This becomes 6a, and then I have 3x minus y, and then I have x plus y. So here, simplification is not just only for writing it more compactly, but it gives you another factor which was not seen in the beginning. This is the final answer to this problem. So I would consider it's a good problem. Okay, first of all, you learn how to factorize expressions like this, binomials, trinomials, or something like that, and then after that, simplification is necessary. After simplification, you should be observant. Might be there is a new common factor that you can pull off. Yes, Sergey? You have questions?
I was going to ask if it was better to factor 3 out or just use an identity if there is one.
Yes, that's what I'm saying. After simplification, might be different things can happen. In this case, I was just able to factor a 3 out. Sometimes you need to use another identities. But because our lesson haven't reached to that point yet, I just might give this example. One thing that I want to also mention is that to see how GeoGebra actually solved this one for us, to see if it works here as well. Okay, so we go here, we go to cast view, and let me just get rid of these other views which we don't need. Okay, I think this, because factorization probably starts with the factor, I just type, no, yeah, it works. So factor is here, I go here and then factor number, probably you can use it for factoring numbers, but factor polynomial is our concern here, yes? So I try to type that one, but you remember we have to put this multiplication thing, and then we have what? 3, I don't think for numbers it is needed, but anyway, y, and then to the power of 2, and then we go down minus 6a times x, and then we have this 3x minus y s, and then finally we go to the last term plus 10 star a star y star 3x minus y.
3x.
Yeah, might be I need that one as well. Yeah, let me just be quotient. Yes, is that right? Let us see what will be the answer. So the answer is 6a x plus y 3x minus 1. Of course, except the order, everything is the same. So this is also, remember that you have this function in GeoGebra as well, because as I told you, factorization of polynomials could be highly non-trivial. Yes, but at least you have this opportunity to use this GeoGebra's application here as well. Okay, so now we want to go to the second trick. The second trick is, of course, the identities we learned. We learned 2 main identities. So one of them is this. Do you remember squaring rule? If I have a plus minus b to the power of 2, the answer is a squared plus or minus 2ab plus b squared, yes? But you see that if the right-hand side is given to you, this is your duty to recognize this pattern. As far as you realize that this pattern is the squaring pattern, you can write the answer. So that's not a new lesson. In identities, I gave you this left-hand side. You were supposed to expand it without pair of brackets and write to the right-hand side, reach to the right-hand side. Here, I just do the opposite. So I give you this. You need to realize this is a squaring pattern and write the answer in front of it. You need to write something so that after being squared, it gives you this. Why this is factorization? Because what is the meaning of a plus b to power 2? It is nothing except a plus or minus b multiplied by itself. So this means that if you write this in this form, you have been actually able to write it as a factorized form because it's a product now. The power of 2 will also be considered as a product. So that is one important thing. And the other important thing that we learned in Math 2C as well is just the conjugate identity. The conjugate identity, I gave you a minus b and a plus b. You wrote a squared minus b squared, but this time a squared minus b squared is given to you. You need to recognize the pattern and reverse engineer that and then write to this, reach to this one. And then you will realize that this is a subtraction, but that's a product, so that's a factorized form. Yes? But because we have already practiced a lot, so let me just give a mixture of questions here. And one thing that I want to mention, this method that I described here has priority over any kind of methods that we will learn later. So whenever you can factor a factor out from all the terms, always try to learn it in this way. Always do it and then think about other methods that might be applicable. Okay, so have this in mind. This factorization method that we just learned before this has priority to any other methods that we will learn in the future. Whenever you can do this, do it, and then think what can you do with the rest. Okay, this is important to have in mind. Okay, so let me just write a mixture of these problems because these are not hard. We have already studied them, and then we solve them together. Okay, so example. So again, factorize. By factorize, I mean fully factorize and simplify if possible. Okay, so number one. So for example, x squared plus 4x plus 4. Do you think we can factorize this expression? Yes, it's a complete square. How do you understand that this is a complete square? The indications are you have two complete squares, but the important thing is that the middle term should be engineered in a proper way. So what are these numbers? One of them, what this is x, this is 2. If I multiply them in my head, it becomes 2x. And then you see the formula is 2 times the first one times the second one. So I multiply a 2 by myself, it becomes 4x, and 4x is exactly in the middle. So this is what I want you to understand. Whenever you have trinomials like this, with two complete squares, you should get suspicious about that might be this is the rule. How you really can confirm that this is indeed the rule? You take a square root of this in your head, it becomes x. Take a square root of this one in your head, it becomes 2. Multiply them, it becomes 2x. But you remember, multiply by an extra 2 because of that formula. And if it works, then everything is correct. So it works here in this case. So what can I write for the answer? I can write the square root of this, x, square root of this 2, and then 2 power. That's the factorization of this, yes? It's very simple. For example, let me give you another one. So number 2, so what do you think about this? 4x squared minus 4x plus 1. Do you think I can also factorize this using the same rule? Again, I have a trinomial. 2 of them are complete squares. But it is not enough yet. I have to check it at least in my head. Take the square root of this, it is 2x. take the square root of this, it is 1, multiply them, you yourself have to multiply by an extra 2, it becomes 4x, yes, this is the middle term with a negative sign. So the answer is something like this. The first one is the square root of this, which is 2x, and the second one is the square root of 1, which is 1. So that's the answer. Yes? So number 3, so I would write 18a to the 4 minus 24 a to the power of 2 plus 8. Okay, what about this one? We want to factorize this. Again, let me repeat this. It's a trinomial, so we might get suspicious that this is going to work, this identity. But unfortunately, it seems not, because for that identity to work, I need to complete the squares. So none of them is. So what do you think I should do here? Yes?
To factorize number 2.
A 2. And I told you, whenever you can factorize any common factor out, that has the priority to every other method that we are learning or we are going to learn. So you see that the first step is not to think about identities or whatever, because it is not hard to see that 2 is a common factor. So do that and then start thinking which method is more appropriate. So I will factor a 2 out. What is left here? It is 9a to the 4. It's minus 12a squared. And then plus 4. Okay? Can I continue more? I have a trinomial here. Now you see that 2 of them are complete squares. But that is not enough on its own. I need to double check. So I go to a scratch paper, take the square root of this in your head. It is 3a squared. Square root of this one is 2. Multiply them, and you need to multiply an extra 2 by yourself because of that formula. It becomes 12a squared, which is exactly the middle one. So now it is a pattern. This becomes 2, and then what I should write for this? The square root of this is 3a squared, and the square root of that is what? 2. Of course, you should also think about, can I factorize this a little bit more? I will talk a little bit about that later. But this is the end of the problem, people. Okay, so what do you think about this one? For example, number 4, I give you x to the power of 3y minus xy to the power of 3. Okay, so here, this is a binomial. So probably there is no hope to think about solving the problem using a squaring rule. But then I told you that the priority is factoring out if possible. And it is here in this case, yes? So you can pull xy out. So the first thing that you do, you take this out. It is already in factorized form. It is a product, but it is not complete yet. Why? Yes, because we have x squared minus y squared, which is a conjugate. Then you have to continue. Otherwise, you will not get the full mark. So this is the end of the story. X times y, x minus y, x plus y. So first one, I applied the first method, and the second one, I used the conjugate rule. Okay, so let me give you some simple example because I want to tell you something. So if I give you x to the 4 minus 4, x to the power of 2 minus 4, can you factorize this? Of course, this is super simple. What's the answer? X minus 2, x plus 2. But what do you think about if I give you x to the power of 2 minus 3? There is something deep going on that I want to tell you about that. Because when I want to factorize, I have to give you the set of numbers that I am supposed to work with. And by default, that is z, the set of integers. If I want to relax that condition, of course I can factorize this, yes? Why is that? Because x squared is a complete square, you might think that 3 is not a complete square. Yes, you are right, it's not a complete square, but I can write it in the form of this number to power 2. because the square root of 3 to power 2 is just 3. And then can I use the conjugate rule here? Yes, indeed you can. The answer is x minus the square root of 3, x plus the square root of 3. So you see, but the number that is involved in this problem is a square root of 3, which is an irrational number. One thing that I want you to understand, are these equalities correct? Yes, they are 100% correct. It's a true equality, okay? But usually in our lessons, when I say factorize this, you should stop here. Because by default, I mean to use only integers as coefficients. This is something, I don't know which rule is using algebra, might be in GeoGebra, we can also ask. This is called the field of factorization. The field of factorization, which field? So the domain of factorization by default is Z. It means that the numbers involved should be integers. Yes?
If you were to work with all numbers, this would just go on forever, right? Because I mean, the square root of x is the power of 2 and so on, right? You could just factorize this forever.
No, that's a different story. If you want to continue forever, now you are changing x to a square root of x.
Yeah.
That's not even, that is not possible.
Yeah, well,
I mean, that's not called factorization. I understand what you mean. No, I am talking about factoring polynomial. If you go further, the factors are no longer polynomials. So that's why I don't consider them at all. But x minus the square root of 3 is still a polynomial. Because you know that a square root of x minus, for example, fourth root of 3, yes, this is not a polynomial because the power of x is 1/2. If you remember the first lesson, we said that the polynomials shouldn't have rational we should have only integers, yes, as exponents. So that's a different story. But this is still a polynomial, but it is a polynomial whose coefficients are coming from irrational numbers sometimes. That's what I'm saying. So whenever we talk about factorization, we are always working with polynomials. It's always. And always by default, we are working with the domain of integers for the coefficients. Yes?
also, x could be negative. X could be negative, and then there's no.
Yeah, x could be also negative. But so what I'm saying is that even if you're allowed to work with real numbers, this is the end of the story. You don't continue. Yes? Because then you will face something which is not a polynomial. Is that clear? Okay. So that's what I'm saying. In our lesson, when I say factorize, it means fully factorize, simplify, and stick to the integers. This is all implicit in the word factorize, yes?
But would you be able so? But if your expression had division,
No, in that case, it's not a polynomial in the beginning. But then it might be you can factorize the numerator and the denominator separately.
Okay.
So for example, even in numbers, what can I say? For example, I say 27, and this is 3, let me get 4, 64. It's not a sensible question to ask factorize this number. Yes? Yeah. This is, or if you think that this is sensible, I need to give you the convention. We don't talk about factorizing a fraction. Yes? We can say factorize its numerator or factorize its denominator. Yes. Okay, so let me just repeat. When I say factorize, I mean fully factorize, simplify, and stick to the whole integers. Yes? But it doesn't mean that this equality is wrong. This equality is right. And if I ask you to do the factorization and you're allowed to use the real numbers, then you can also write this. And by the way, let me check GeoGebra. Might be in more advanced programs, you can actually tell the application in which domain you want to do your factorization. But let me just test the idea here. So let me just ask GeoGebra to factor just the standard one. x to the power of 2 and then come down minus 4 for the time being. So this is the factorization. Yes? But now let me ask GeoGebra to factor this expression. So factor this one polynomial. This time I want to write x to the power of 2 minus 3. Yes? It returns the same thing back. Yes? It gives you x squared minus 2. So by default, GeoGebra is also factorizing in the set of in the set of integers. But I just want you to know that GeoGebra is aware of this one as well. If I write this minus a square root of 3 and then multiplied by, I don't know, multiplied by x plus square root of 3, yes, and then if I ask GeoGebra to expand this, is this expansion? It seems so. No. What's expansion? So what does it mean? So do you remember which one was expansion? Let me just... Please check your input. Yes, please?
Or do you write expand and then the expression?
Yes, but I was thinking this is expand, isn't it? Anyway, so let me just write expand. You are right. Yes, expand, and then probably... yes. Let me see how it works now. No, there's something...
It doesn't want to do that.
Oh, might be I shouldn't put this dot here now. It is inconsistent. Now I took the dot out, it worked. But it's a little bit strange. Anyway, but you see that at least x minus square root of 3 times x plus square root of 3 is indeed x squared minus 3. So what we have written on the board is correct. But I will not give you this to factorize. If you are supposed to, if you got this expression somewhere in, don't continue. Because by default we are working in the set of integers. But I want you to understand it's a relative concept. I should be able to give you, it's a good idea if you can search the web, I will do it later, to see if we can give the domain of factorization to GeoGebra as well. But I know for more advanced softwares we can do that. Okay, anyway, let us go back to the lesson. Give you more examples. What do you think about this one? For example, x to the power of 4 minus 81. Can I factorize this? So remember, for conjugate pattern to work, you have to have the difference of two complete squares. Yes? You have to have the difference of two complete squares. Can I use the conjugate rule here? Yes, because I have the difference of two complete squares. So if you want to write all the details, you need to imagine x to the 4 as a complete square. You need to imagine 81 as a complete square. And then you have the difference of two complete squares. So the answer would be x squared minus 9 times x squared plus 9. Yes? And now again, can I continue or should I stop? I continue only for the first one, which is another conjugate pattern, which becomes x minus 3, x plus 3, and then I have x squared plus 9. About the sum of two complete squares, I want you to remember that this is not usually factorizable, unless you are allowed to work with complex numbers. Okay, so it means that you have to expand your domain from Z to the set of complex numbers, because if you are allowed to work with complex numbers, there is a nasty number called I. When you raise it to power 2, it becomes minus 1. And in that case, you can continue, because x squared plus 9 can be written as x squared minus 3i to the power of 2. Why? Because 3 to power 2 is 9, I to power 2 is minus 1, so it becomes minus 9. There is another minus sign, I intentionally put them there, it becomes positive 9. And then it becomes a difference of complete squares again, but in the realm of complex numbers. So then it becomes x minus 3i, and then x plus 3i. Okay, I'm just giving you this information for your general knowledge. You really don't need to bother about it. End of the story is here, but I just want to tell you that if you have the difference of complete squares always remember about the conjugate rule. But whenever you see the sum, the sum of two complete squares, that's the end. You don't need to continue. Because if you want to continue, you need to work with complex numbers. Okay. So what do you think about this one? 3x to the power of 5 minus 48 xy to the power of 8. I want to factorize this. So what is the first step here?
Factorize 3x.
Yes, you see, you might say that this is none of these patterns. You are right. This is neither a square pattern nor a conjugate pattern in this form. But remember, I told you the first trick we learn has the priority. So I can factor something out. From numbers, I can pull a 3 out. From the letter parts, I can pull an x out. So what is left for me? So I just pull 3x out. This becomes x to the 4 minus 16 y to the 8. Okay? It is factorized now, but might be it is not fully factorized. Yeah, you realize that you have the difference of two complete squares. So you have to carry on. So this becomes 3x. The square root of that one, x to the power of 2 minus the square root of that one, 4 y to the power of 2. But x to the power of 2 plus 4y to the power of 2.
Y to the power of 4.
Oh, yes, thank you. It's 4. Thank you. Okay, is it finished or not?
No, there's another.
There is another conjugate pattern here. So I just continue. So then it becomes 3x. It becomes x minus 2y, x plus 2y, x to the power of 2 plus 4 to the power of 4y to the power of 4. And that is the end of the story. So I want you to understand, we are not making things simpler. Might be you say this is even simpler than my answer. So be careful. The goal of this lesson is not to make things simpler. Yes? It's more complicated than that. But the point is to write this expression as a product. Yes?
Shouldn't be x minus 2y squared.
Oh, I am very confused today. Thank you for correcting me. Thank you. Yes, thank you. Because the square root of this is x, but the square root of 4 is 2. The square root of y to the 4 is y to the 2. Yes, thank you. But you might say that, okay, why we bother to do this? That's a good question. Why we bother, for example, I can give you two answers. Why we really bother to factorize a polynomial. I can give you two answers. I don't know what you have in mind. Yes, Ali?
It could help with solving a second degree equation.
Not only second degree equation, but you are right. If I can factorize, if I give you a higher degree equation, it's extremely hard to solve it unless I somehow can factorize it. If I can factorize, then because of the zero product rule, I can solve an equation. This is one reason that we really like to factorize polynomials. Another reason?
You can use it to cancel terms.
Yes, if in the future, here, for example, if I want to, for example, you know that if you want to write 15 over, for example, 9, you know that you can simplify it. It was so simple for you, you do it in your head. But the reason that we could do it is because we factorize 15, we factorize 9, and then we cancel the common terms. But because it was so simple, you don't even care about it. The reason that we can carry on is because we can factorize the numerator and the denominator, which is the main important reason that we are refreshing your memory about factorization. In the next lessons, we want to learn how to simplify rational expressions, algebraic expressions containing polynomials, and we want to know how to add them, subtract them, multiply them, and divide them. So that's a very important part of the chapter 1 lesson. Okay. So, but anyway, at least you have two good reasons why we are interested to factorize polynomials. First, solving higher degree polynomial equations. Second, simplifying expressions. Yes? Okay. So this means that momentarily I make things complicated, but the benefit will come later that I want to simplify things in the future. Yes. Okay, so there are some other things about factorization I want to talk about today, and that is the common term identity. Do you remember we had this before? I remember we practiced this together in Math 2C. So let me just refresh your memory again. Do you remember that was based on guesswork? Guessing two numbers whose sum is this and the product is this. Do you remember that was the content of the common term identity? So for example, let me just write this common term identity here. That was x plus 8, you remember? I want to multiply two binomials that share one term with each other, and then you want to multiply these two. You will say that common term squared, the sum of the non-common terms multiplied by the common term, and the product of the non-common terms. So that is expansion. But factorization is the other way around. I give you the right-hand side, you have to recognize the pattern and write the left-hand side. Because the left-hand side is in a product form, yes? Yeah. So now you see that whatever you see here is the sum of the uncommon terms. And what you see here is the product. So let me call it S, and let me call it P, the product. So then I will rewrite this in this form. X squared plus S times X plus P. So whenever I want you to factorize this, one method you learned, that was the first identity, yes? If this is complete square and this is complete square, and you are lucky enough that this one is the square root of this times 2, then you use the squaring rule. Other than that, it is always good. Here, we do some guesswork, and later I will tell you systematically how to do it, okay, if you cannot find the numbers. Because if the numbers are complicated, even I myself cannot guess those numbers. But if you can guess, this is the simplest way to factorize this. Whenever you see a trinomial like this, and let me emphasize here that this coefficient is 1. I would recommend you to write it with a different color, so you see that this method only works if this coefficient is 1. Then you need to ask yourself, can you find two numbers whose sum is this number and the product is this number? As soon as you get them, you put them in this formula. Yes? For example, can I factorize this? X squared plus 5x plus 6. Yes? I ask myself, can I guess two numbers whose sum is positive 5 and the product is positive 6? It's very simple, 2 and 3. So what you do, you write x plus 2 and x plus 3, end of the story. Yes? Okay, so let me write some of them here on the board, do it together. So let me just write them and you tell me what to do, okay? X squared minus 8x plus 12. So what should I do? I hope that you see the pattern is the same, and this is important. This is 1, and minus 8 is playing the role of S, 12 is playing the role of P. So I want to find two integers, because by default I am supposed to work in integers. Two integers whose sum is negative 8, the product is 12.
Minus 2 and minus 6.
Minus 2 and minus 6, agree? So what you just need to do is minus 2 and minus 6. Minus 2 and minus 6, when you add them, it becomes minus 8. and you multiply them, it becomes 12. That's the factorization. Another one. X squared plus 10x plus 16. By the way, this is a good example if it works. I don't know, hopefully it works. This is a trinomial. How many complete squares you see? 2 complete squares. So you might get suspicious at this point. This is the first identity. But if you just naively write the answer, that's correct. That's not correct, because you might jump into the conclusion that, okay, this is this one. But that is not correct, yes? Because 2 times the first one times the second one is supposed to be 8x, but this is 10x. Okay, so it doesn't work in that way. But I don't know if there is any other way to calculate. Can we have 2 numbers whose sum is 10 and the product is 16? Very simple. 2 and 8. So be careful about this. So 2 and 8. Yes, 2 and 8. X plus 2 and x plus 8. So that's a good example, because if you are in a hurry, you might write the answer x plus 4 to power 2, which is wrong. Okay, another one. So I can make, I don't know how much you have good friendship with numbers, but can you guess these numbers as well? Let's see if I used to be able to guess, but I don't know if I can do this now. Can you think about 2 numbers whose sum is negative 22 and the product is 85? By the way, so if I recommend you to go with 85, it's not hard, by the way, to guess, but if it is hard, just go and factorize 85. So you divide by 5, how many times? How many times? 17, yes? And then you divide by 17, it becomes 1. And then you get 2 numbers whose product is 85. Have they some kind of relation with 22? Yes. If you add them, it becomes positive 22, but you need to adjust the signs now. So what I do, I would put x here, x there, and then I know that somehow these numbers should be involved. So I put 5 and 7. Now I want you to adjust the signs. Should be, both of them should be negative, because the sum is to be negative 22 and the product should be positive 85. So if the numbers are big, that's also possible. But again, if the numbers are really, really big, you cannot, for example, ask computer to guess. You need to have a decisive algorithm. And that decisive algorithm comes later. I will talk about that later. Now, by the way, I can talk about this just right now, okay? But let me give you more examples, and we can talk about this systematic way right now. Okay, can you guess about this? By the way, these are good examples. Usually I write them together. It's a little bit confusing. This one, the numbers are super simple, and this one. Do you have any clue? The numbers are intentionally very simple. So what is the first one? You need 2 numbers. You need 2 numbers whose sum is negative 5 and the product is negative 6. What are those numbers? Yes?
Negative 6 and 1.
Yeah, positive 1, negative 6. It has nothing to do with 2 and 3 in this case. Yes? Is that understandable? Because if I add them, it really becomes negative 5. If I multiply them, it becomes negative 6. What about the second one? Minus 2, minus 3. If I add them, it becomes minus 5. If I multiply them, it becomes positive 6. What about this one? X squared plus 2x, 20x plus 19. Can I factorize this? And what about this one? This is not teaching. I am just trying to convince you. You can also guess most of the time.
1 and 19.
This is 1 and 19, yes? X plus 1, x plus 19. I told you, just start from 19. What are the numbers whose product is 19? You don't find any others. There's 1 and 19, and then you're lucky, because if you add them, it becomes 20. What about this one?
4 and 8.
But you need to adjust them. So for example, 32 is 2 times 16, but 2 times 16 is hopeless. There is no relation between 2 and 16 if I add them or subtract them with minus 4. Another pair that comes to mind is 4 and 8. 4 and 8 is good, yes? Because it has some relation with this 4. So what you do, if possible, you write a 4, you write an 8, and then try to adjust the signs. So what are the signs?
Positive 4, negative 8.
Positive 4 and negative 8. Because the product is negative, one of them should be positive, one of them should be negative. Because the sum is negative, it means the one which is negative should be bigger. That's the reason. Anyway, but you might ask what happens if I have some numbers here. So do you know the systematic method is to use this formula. So if you have a, x squared plus bx plus c. And if you want to factorize it, the formula is this. It's a, we can prove the formula of course, but this is the formula. Yes? This a is exactly the a that appears here. You might say, what is x1 and x2? x1 and x2 are the roots of your polynomial. Yes? So x1 and x2 are these numbers. Yes? So this is the general formula for factoring a. It's a good idea to think about why this is correct. It's good to be able to prove this formula. Because this is a systematic way. So this is an algorithmic way. You can write a computer code to factorize any second degree polynomial that you actually provide for the calculator. Yes? It's a good idea to try to prove this formula. Now, why this formula is correct? Yeah, let us just do this to understand this. By the way, this is in the book a little bit later. So let me just prove it right now, and then we can skip that when we reach there. And I wanted to memorize that because this is the end of the story of the second degree polynomials. Yeah, please keep quiet. Thank you. Okay. How should I prove this? I start from the right hand side and multiply them to see that this becomes the left hand side. So what we need to do, now we have a good identity in our hands, yes? 8 times x minus x1 times x minus x2. What type of identity is this? This is the common factor identity. Common term identity. So I copy and paste this a part. The common term identity will tell me the common term squared, the sum of the non-common terms, which becomes minus x1 plus x2. I pull the minus sign out, multiplied by the common terms, plus the product of the uncommon terms, which becomes plus x1, x2. Yes? Everyone agrees? If you just multiply them, this is the result. And by the way, I don't know why this is missing in Swedish curriculum. There are two important formulas I want you to know. I know in Math 4 they are using it in the problems without even mentioning it. It's good to know it. There is a formula for the sum of the roots and the product of the roots. And that is very simple to understand. These are my roots. Once I add them, once I multiply them to see what I get. Let us just do it together. So x1 plus x2. Let me answer this question. x1, for example, is this one. This is my x1. It doesn't matter which one I choose to be x1, which one to be x2, but let me write it in that way. So tell me, do you agree with this? I am telling you that x1 plus x2 can be written in this form. Yes. But now what happens? Very simple thing happens. This square root, whatever it is, it comes with a negative sign here. The same square root comes with a positive sign. So and the denominators are the same, fortunately. So what I write 2a. And then I start adding the numerator to the numerator. This part and that part are gone. I have minus b, which becomes minus 2b. But then this 2 and minus 2 can be simplified, so it's just minus b over a. So it's a very good relation. I don't know, in every education system I have seen that this is part of the lesson. But anyway, let me just write it down for you here. So x1 plus x2 is minus b over a. Of course, we are always interested in the roots themselves. But if in some reason, if I ask you what is the sum of the roots here, what is the sum of the roots? It's minus 20 over 1, which is minus 20. And that's correct, because the roots are minus 1 and minus 90. So that's a formula that provides you this opportunity to answer the sum of the roots without knowing the roots. Yes, from the equations. Now the other one is a little bit more tricky, but let us just do it together. So x1 times x2. Let us do that one. So this means that I will take this one and then multiply it by that one. Okay, and then you tell me how to continue. I have a fraction multiplied by another fraction. So how should I multiply fractions? I have to multiply the denominators, which is simple. But I have to also multiply the numerators. But can you detect the pattern in the numerator when you multiply them?
Common term.
It's no better than that.
Is it conjugate?
It's a conjugate rule, yes? Because you have minus b, you have this square root, the same square root, once added, once subtracted, and you want to multiply it. So the answer becomes the first one squared minus the second one squared. The first one squared becomes just simply b squared. Minus, if I square this one, this 2 will kill this square root sign. It becomes b squared minus 4ac. Divided by 4a squared. And then I multiply this minus sign in. The first one becomes negative. The second one, which was negative, now becomes positive. Divided by 4a squared. And then again, this part and that part is also gone. And then I am left with 4ac divided by 4a squared. Moreover, so this one and that one are also gone. A and one of these a are cancelled. I am left with c over a. So that's also nice to remember, especially the people who want to join these contest problems. These are very famous things for quadratic polynomials. So if I have a polynomial, by the way, these are under which conditions? Under the condition that we have two roots. So it means that the discriminant should be positive. So if you have a polynomial who has two roots x1 and x2, if you add them, it becomes minus b over a. B is this coefficient, a is this coefficient. If you multiply them, it becomes c, the constant term, divided by this term. Okay? Now let us go back to our to the proof of the formula. My goal was to prove this formula. I started from the right hand side and I expanded that. Now what is appearing here, I calculated here up there. What appears here, I calculated that for you there. And then I just substitute them, okay? So you can just put them in a box, assuming that you know this. I continue again. So this becomes equal to, you see here I have a, and then I have x squared. What can I put instead of x1 plus x2? x1 plus x2 is minus b over a. There is also a minus sign here. It becomes plus b over a. And times this x here. Yes? And then plus c over a. x1 times x2 is c over a. Now it is finished, yes? Now you take this a, which is outside, and multiply it in. What happens? It becomes ax squared. The a that I am multiplying here will cancel this a down there. It becomes bx, yes? And then finally the last one. The a that I am multiplying here will cancel that a, and this is the c. So this means that I started from the right-hand side, and I continued, and I reached to the left-hand side. So the right-hand side is equal to the right-hand side. So that's the proof why this formula works. But this is, I want you to see, this is not based on guesswork. If I give you a second-degree polynomial, no matter how complicated is that, you take your calculator, you calculate these numbers, and then put them in this formula. So you will have your factorized form of your expression. For example, let me give you an example, and then I will stop. I will continue one more session, or at least half a session with factorization before moving to the next lesson. Because might be you are tired now, I just expected to stop after this example. So let me, for example, try to write this. So 7x squared plus 8x negative 15. So for example, we want to factorize this. To be honest, this is not one of those problems that I can immediately understand. Might be you can do some guesswork. If you can, just do it, okay? But if not, this is the example I want you to see. If you cannot do the guesswork, then you can do it systematically. Be careful. I am asking you to factorize. It has nothing to do, the question has nothing to do with solving equations. But because of the method we developed, we realize we have to solve equation as well. But this is the reason. So the question, I don't want you to get confused. Factorize, end of the story. There is no equality here. The expression is given, and I'm asking you to factorize this. If you can do it in your head, just be my guest and do it. Otherwise, I am just telling you the algorithm. This algorithm tells you that this blue pen is the solution using this algorithm. So this, I myself put the equation equal to 0. Be careful, equal of 0 is not in the problem in the beginning. So what I do, then I would write x1 and x2 are equal to minus b plus or minus this number squared, 64, 4 times this times that, which is minus, it's plus 420, yes? I multiply this by 4 first, it is 60, and then 60 multiplied by 7 is easier. If you multiply 4 by 7, it becomes 28. 28 multiplied by 15 is harder. Okay? But the answer is 420. And then divided by 2 times a, which is 14. And then this is hopefully a good number if I haven't done any mistakes. 484. Yes, I think this is a complete square, isn't it? It is 22, isn't it?
22.
Yes? Let me check. Yes, 22. So it is 22. So it is minus 8 plus or minus 22 divided by 14. It might be the numbers are big, but at least even if the numbers are very, very big, I don't have any problems because I can use a calculator using them. I have the algorithm. So then I have 2 roots. One root, so I call it x1 for example. Minus 8 minus 22 is minus 30 divided by 14. I do not stop here. It becomes minus 15 over 7. This is a bad sign already because I told you that by default we have to work with integers. But this is a rational number. But you have to be patient a little bit. And then x2 is what? Is 22 minus 8 is 14 divided by 14 is 1. Okay, and then I put everything in the formula. So this expression is equal to a, which is 7 multiplied by x minus x1, which is minus 15 over 7, which becomes positive 15 over 7. And then I have x minus x2. If you stop here, that is not wrong, but you have factorized this on the domain of rational numbers. Yes? Minus 1, sorry. It is not wrong if you stop here, but which number, 15 over 7 is not an integer, is a rational number. So this form of factorization is valid, is acceptable if you are working with rational numbers. But I told you by default, we're supposed to work with integers. Is there any way to factorize this in integers or not? Just multiply the 7 in. Yes? So what happens? It becomes 7x plus 15, and then I have x minus 1. I have seen many of you students can guess this. It's not probably that hard. You start from here. Instead of writing 1x here, 1x there, you ask yourself, how can I write 7x squared as a factorized form? You write 7x here and x there and try to engineer it a little bit to get those numbers. But the point is, I want you to understand this is an algorithmic way. So if you know a language, you can just code the program to follow this, and no matter how the numbers are big, you can immediately factorize them. So this is the lesson that we don't need it now, but we need it a little bit later. But I will consider this as already being taught, okay? I will just take one more or half a session next time to complete the factorization so that we can move on. Any questions? Yes?
Is that formula? Is that on the formula sheet?
I don't think so. By the way, I will put the formula sheet on the Google Classroom so that you can see which formulas are there and which are not there. Okay? Any other questions? Okay, thank you.